Hello and welcome back. In this example, we're going to find the area under the graph of 16 minus x squared. That is between the vertical lines x equals 1 and x equals 4. That is going to be above the x-axis. And to do this, we're going to go through and use infinite sums to do this. So our area is going to be the limit as n goes to infinity of the sum from I equals 1 to n of the area of each of these smaller rectangles, which is going to be f of m sub I, which is the height of the function, and it's the minimum height on the interval x sub I to x sub I plus 1, times delta x, which is the width of each rectangle. And so to do this problem, we're going to kind of set it up with a graph first to kind of see how we're going to label all of our rectangles. And so to do this, we're going to draw a graph of our 16 as our y-intercept down to 4. And again, our parabola, of course, goes down like so. But again, for us, we're going to actually start at 1 and find the area under the graph from 1 to 4. So again, to do this, we're going to draw rectangles. And the easiest way to do this, of course, is to go through and draw a bunch of vertical line segments under the graph, and then determine if you want to use underestimates or overestimates. So we're going to use underestimates, which means our first rectangle is going to be having this height here. And again, we continue this all the way across. And so in doing so, we're going to have the area of each of these rectangles summed up. And so each of our x sub I is going to come from taking these values here. So we're going to call this one x0, call this one x1, x2, all the way down to our x sub n, which is equal to 4. And then we're going to go through and write a formula for these. So before that, we're going to have our delta x, which we always know is b minus a over n, which is the width of our interval, which is 4 minus 1 over n, or simply 3 over n. And now we're going to figure out how to get to each of our m sub i's. So the m sub i's, because our function is decreasing, will be the 1 plus I times the delta x, which is going to be 1 plus 3 times I over n. So we're going to substitute these two quantities into our limit calculation and then algebraically work everything out as far as we can. So my area is going to be the limit as n goes to infinity of the sum from I equals 1 to n. And my function is going to be, actually, I'm going to write the function later. So that's going to be f first of 1 plus 3i over n times my delta x, which I know is 3 over n. And now I can substitute in the actual function for this problem, which we know is going to be 16 minus, and again, our x is 1 plus 3i over n, and that whole x value is squared, and that is times the 3 over n. And now we have to algebraically work this out. And in doing so, we have to make sure we are very careful with our algebra. That's going to be 16 minus the quantity. And if we imagine ourselves foiling this out, we're going to have a 1 times a 1 makes a 1. And then we're going to have a 1 times 3i over n, and another 1 times 3i over n, making 6 times I over n. And then the last term is going to be 9i squared over n squared. And again, that is still multiplied all by the 3 over n. All right, so we can now start cleaning this up a little bit. So we're going to have a 16 minus 1 minus 6 times I over n minus 9i squared over n squared. Again, it's still times 3 over n. That has not gone anywhere yet. And then that'll be the limit as n goes to infinity, sum I equals 1 to n of 15 minus 6i over n minus 9i squared over n squared times 3 over n. And we might as well go through and multiply in that 3. So we're going to have, what, 45 over n minus 18i over n squared minus 27i squared over n cubed. And from here, what we want to do next is break apart each of these sums and factor out the constants. And again, in the summation process, the I is the index and n is a constant. So this is going to be the limit as n goes to infinity. And we're going to have 45 over n times the sum from I equals 1 to n of just 1 minus 18 over n squared, the sum again from I equals 1 to n, but now of the index I, minus 27 over n cubed, the sum from I equals 1 to n of the index I squared. And again, we're taking the limit of this whole expression as n goes to infinity. So next up, what we can do is substitute in the closed form formulas for these sums. So we know that the sum from I equals 1 to n of the index 1 is just an n. So we'll substitute an n in there. And these parentheses are getting a little wonky looking, so let's kind of put them back in nicer looking. And again, so that's an n minus 18 over n squared. The sum of the first n integers is n times n plus 1 over 2. And then finally, the formula for the sum of the first n squares is n times n plus 1 times 2n plus 1. And that is over 6. And now we need to simplify this down. So the first term, of course, that's just a 45. In the second term, we'll notice that we can cancel out this n with one of those n's down below. And we can also rewrite 18 over 2 as just 9. So that's going to be minus 9. And that's going to be n times n plus 1 over 2, which is now the 2's gone. And it's n plus 1 divided by n. Simplifying that out, that's going to be 1 plus 1 over n. And then back here, what we can do is reduce this down as well. We can go through and we can strike out one of those n's to make that n squared. Cancel out that n. And then we can reduce 27 divided by 6. And dividing each of those by 3, we can get, what, 9 over 2. So that's going to be minus 9 over 2. And then if we multiply the inside out, we're going to have 2n squared plus 3n plus 1 all over n squared. And so this is going to be the limit as n goes to infinity of 45 minus 9 times 1 plus 1 over n minus 9 halves of 2 plus 3 over n plus 1 over n squared. And now we can take our limit as n goes to infinity, and we will see that 1 over n, well, that's going to go to 0 as n goes to infinity. So will the 3 over n go to 0, and so will the 1 over n squared go to 0. And that's going to leave us with a number 45 minus 9. And then if we have 9 halves times 2, that's going to be minus 9 again. And so that's going to leave us with 45 minus 18, which is really going to be 25 plus 2, which is 27. So there's 27 units of area that are below this graph using this infinite sum process. And going all the way back to the beginning and kind of doing a quick recap, you'll notice that we went through and we drew a quick sketch of the graph. We calculated the width of each rectangle, delta x. We then used a generative formula to find each of the partition points, the x of i's, which is 1 plus I times delta x for a decreasing function. We then substituted those into our function, into our summation formula. We then evaluated the function at those points and went through and did some very careful algebra to take this all the way down to a function that we could take a limit of, and that gave us the value of 27.